We're waiting for a few people to join, then we'll start. Okay, so we'll start with the week 8. Uh, week 8 content. So in week 8, we are mostly discussing IP and stuff. So it's mostly IP routing, introducing then IP address allocation. Then there is scalability, host, packet forwarding, and stuff. So what I'll do is that I'll go through the assignment first and see which topic need to be covered in this live session, and then cover the things accordingly. Uh, so I'll just go through the assignment question, and decide the topic which discuss that. Then I will discuss the topic, and you'll probably get your answers from that. Hopefully. Okay. So okay. So question number 1 is based on this IP address allocation. We'll learn that, but it's a bit far in the course. Today's topic: why do we consider dividing an IP address into network address and host address? We'll do that now. Yeah, IP division, or you can say representation. Third one is whether the following statements are correct. It's about the internet. Fourth is the following network. What will be the routing table for C? Who is link state routing? Okay, link state routing. Fifth is in the BGP protocol, update and notification messages are used for. We'll see BGP. Sixth question is also BGP. Seventh question is also BGP. Eighth question is OSPF. Nine is uh, hmm, routing. Tenth is okay. We start with the first thing. The IP address. So when you see a computer, it has a IP address. Let's say IP1. Okay. There is another computer. There is IP2, and these both are a part of network. And this network has a router, and it is connected to, let's say, internet. The difference that this thing creates, because if you say internet is basically interconnection of network, interconnection of network. So basically, when this IP address thing started, uh, so so since this network is internet is connecting networks together, so internet connects networks, not host networks, not hosts. So that's why that's where we sort of think about uh, giving an address to a network or a group of hosts. So this is a group of hosts. It's not a host. This is a group, the group of hosts, and uh, uh, so this is not a network. This is a group of this is just a group of hosts and not host. But but we cannot just assign IP address to computers. Then we have to assign a IP address to the I mean some sort of address to the network as well. That's why that's how this the notion of network came into picture, where we call this some sort of call it LAN. That means local area network, and this connection, like if there is something like this, like there is a network and there is a router and there is a router again and there is a router 3 and there is another network. uh, we can also call these parts like wide uh, sorry, wide area network, and this is also called WAN. So anyway, so to follow the point, to automatically choose the so anyway, so uh, basically, like whenever you are discussing about a network, you sort of starts with uh, IP addresses, and each host has an IP address, and each um, network has an IP address. That's called network IP or network address, and each host inside that network will have a IP address as well. Those will be private IP address, not public one, but this will have an IP address as well. So, the typical notation of a IP address is like this. So, it's a notation IP notation. So IP notation is like this. There is a four, there will be 8-bit here. Let me just write it like 192.72.0.199. You see each of these numbers, they range between 0 to 255, and that is equivalent to 8 bits. Okay, and so total is 8 into 4, that is 32 bits. Okay. Total there is 32 bits, and it is represented like this. Uh, Something like this. It's an example of address. Okay, so this is done. Uh, then comes the scalability. So then comes the scalability. So then comes the scalability. So the scalability issue is that the scalability issue is like now if there is a router, uh, yeah, so now if there's a router, uh, let's say if there is a router here and a lot of hosts is connected to these routers, host 1, host 2, host 3, host 10. So all these hosts will have their own IP address. So it will be like IP1, IP2, IP3, IP4. Sorry, not IP4. It is like IPN. If these things are arbitrary, so if this um, uh, if this hosts are arbitrary, then each router will have a lot of information to keep, because if there is a packet coming to this router, the router has to know, whether should I put put this packet to this network or just let it go. That's why, so to if it has to maintain a lot of records to have that flexibility in terms of where to send the packets and stuff. So to solve this issue, we people came up with this interesting idea of standardizing the way we write IP address. So there are two way of allocating IP addresses. One is classful addressing, and second one is classless interdomain routing. So first we'll do with the classful addressing. Uh, so classful addressing. The classical addressing, uh, all these IP addresses are divided into class. So there is class A, class B, class C, class D, class E. So in class A, uh, like eight, they're like very large 8 blocks, and mm, wait a second, 24. Yeah. So it's like it starts with 0, and it has first 8 bits is dedicated for network. So let me just draw like this. The first 8 bit is a network, and then is host, host. This is 8, 8, 8, 8. Okay. So what they're saying is that first 8 bit will be used to identify a network. Like if this is the network and this is another network, and these both are using class A, then the first thing it starts with should be start with 0, and the first 8 bit 11010000. Let's say this is 0 1101 0001. So this will uniquely identify these two numbers. So this is 0 here, this is 1 here. That's why these two networks are different, and they both follow class A. This is classical addressing, and they both belong to class A. Then uh, uh, yeah, so uh, yeah, they both belong to class A. They have like, so the total number of network it can represent. So total network will be equals to 2 to the power 7, because 0 is always fixed, and how many possible hosts that can, how many possible combination that you can get of 7 bits is 2 to the power 7, and total number of let's represent it like this. uh, Number of hosts is equal to 2 to the power 7. Number of sorry, this is number of networks, and number of hosts will be equal to 2 to the power the rest number of bits is 24 to the power 24. So it's assuming that this type of network will be having like 2 to the 7 number in the world, and each network will have huge number of computers host within it as to the 20. Similarly, like the B should start with 0, sorry, 1 0, and the number of the number of hosts should look like this. Should be like network, network, host, host. Should be like 1 1 0. Then it should be like network, 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 host, and class D is used for multicast group. Starts with 1110, and these are for reserved, and this starts with 11110. So this is a way uh, of like addressing your addressing your um, like this is a way of classifying and organizing the IP addresses. So the benefit that you will get from here is that, let's say a network is so if I give you a IP address, you'll be able to now tell like to whom this IP address belongs. Let's talk about the class A one because we have draw it. I've already drew it here. So let's say this is the IP address, and this after this there is 192.0.0 dot 192.0.1. Okay. Uh, let's say this is the uh, uh, address of the network. So the address of the network gives us the first IP address that it can from where the host in the system starts. And if you pick up any host in this network, any host, so its IP address will start with this one 01101 0000, then anything, and its IP addresses will be starting with 0110 100 0. Oh no, I mistakenly did 9 zeros. Anyway, like 810. Uh, to be 01101 001 dot anything. So if a packet is coming to this router here, these two networks are connected to this router, and packet is coming through here, and its address is 001 and some other fields here dot anything here. Let's write down the address entirely for your convenience. Like let's the address is 0101001. So either address is this packet will straight go to here. This router will not think about anything because it saw the starting address is this, and this is the network address because this is the class A class of network, and the first 8 bits represents the network. Whatever address that is present after this point should be inside this network somewhere. Maybe here, maybe here. We don't know, but it should be inside this network. That will it will just redirect it to inside that, and the router inside this network will decide where to send this. There is a router inside this network as well. Okay, so this is the benefit that we got from representing this uh, uh, IP addresses using this notation. So then we did a bit of uh, then we did something called CIDR notation, the classless interdomain routing. I'll discuss about this CIDR notation in a minute. Give me 2 3 minutes. I'll discuss that. Hello. Yeah. So the second thing is CIDR notation. CIDR notation says that if there is a IP address, I need to let's say like you are setting up a new network like this, and you have a router and is connected to outside world. First, you need a set of IP address for your systems. Like uh, you need a range of IP address or a what do you call it, a block of IP address, block of IP from your ISP or internet service provider to uniquely identify your network, right? So what it will do is that based on the number of hosts that you can that you're gonna keep, it will it will give you a block of IP address that will look like this: 192.192.172.1/24. So when you say /24, that means that first 8 bits will be used for first sorry 24 bits will be used for networks. The last 8 bit will be used for hosts. Okay. So this is the like it's very easy now. So you can just we can just uh, start by start like giving out uh, IP address block to random people. You don't have to worry about how these things turns out in the future. Like you don't have to be worrying about how these like the block of IP address is affecting uh, the way you allocate them. Is because it's very straightforward. Like it's very straightforward in the way that so if there is a smaller network, if there is a let's say like if you're getting your IP address for your home, so you don't need a lot of hosts in your home, right? So you'll have maximum of 7 to 8 hosts in your home. That will be like a computer, smartphone, anything. So that's why you need around 7 or 8 IP address. And to allocate 7 or 8 IP address, you need 3 bits, right? You need 3 bits to represent 8 things, that is 000, 001, 010, 011, 100, 101, 110, 111. So 1, 2, 3, 4, 5, 6, 7, 8. So you need 3 bits. Okay. So that's why your the IP address that your um, um, internet service provider will give you will be something like x dot x dot you're like something x class. Instead of 24, you'll get 29. So first 29 bit will be for host representing your network. Last 3 bit will be used for your. So this will be for your network. This is for your host. Okay. So network and host. So that is a way of representing the CID notation. Hmm. What is the next thing? Let's just look up where we have to end host summary. Okay. So first thing is that how do you get this IP address? So how do you get this IP address initially? So there is something called dynamic host configuration protocol. It's called DSCP. That translates to dynamic host configuration protocol. Um, uh, so what it does is that when you start a system, it will uh, give you a block of address, uh, uh, block of IP address or its own IP address as well as the gateway's IP address to which network this belongs. So uh, it will it will ask for this, and this DSCP or the dynamic host configuration protocol, it has a pool of IP address. So IP1, IP2, and so on. It will pull one of the IP address out of this collection and give it to you like this. So so when your system is new, like and you don't have any IP address just turning on your system, you just connect into your internet. How do you know it's your own IP address and which gateway to use, like which router to use to send your packets to the internet? Um, then you need a DSCP protocol. So okay, so with that we completed 2 questions, I guess. Uh, um, 2 questions. Let me see. Which questions did we cover by this discussion? Mm, okay, so I think we covered this one and this one. I'll go to the next question. Hmm, uh, the question, not sure about how they, uh, to which, to whom they are referring as, but inter-domain routing. Okay, so let me just cover that first. Uh, Classical addressing CIDR, packet forwarding. Address separate entry to 57 addressing. Uh, CIDR longest request match forwarding. Game algorithm. Patricia tree. This. Hmm. Okay, so we'll start with the routing protocols. Yeah, routing protocols. Uh, yeah, so let's go to routing protocols. So routing protocol states that like if there is a router, and there are different things connected to it, and if there is a packet that comes to this router, which way it will forward this packet. There are a lot of ways, and how to know which way to forward and how to uh, decide where to forward. And uh, so, what things that need to be maintained in the router? Um, what is best for the packet? Which way is the better, and all sort of things. Uh, Stable routes are often preferred over rapidly changing ones. Okay, routing algorithms, optimality, scaling issues. Uh, okay. So there is two way of forwarding or routing packets in the internet. There is first one is the routing method, and second is the next stop method. There is also host specific and network specific methods. Uh, for the host is based on the network specific methods. Hmm. So if there is a network like this here, there's a host one, and there's a network one, and there's a router, there is a network two, there is another router, there is network three, and there is host two. Okay, this packet is coming from this to this. So there's something called routing table. The how the routing table, the destination. If we create a routing table based on the host, it is routing table based on the host. Sorry, based on route. We'll start with this like for at H1. Um, H1 the routing table would be, let's say it's called destination, and then route. Destination is host 2, route is uh, router 1, router 2, host 2. So they let this called router 1, this is router 2. Okay. The routing table at router 1 would be destination is host 2, path is route 2, host 2. The table at router 2 would be destination is host 2, route is route directly host 2. Okay. But if you consider based on next stop, so routing table based on next stop, this is next stop. at host one, it will be like there's destination and there is route. Outside, not route. It will be next stop, next stop. So destination would be H2. Next stop is router one. Router one will be H2. Next stop is router two. Router two. Destination is H2. Next stop is H2 as well. Or you can put like this dot dot. Okay. Okay. And if I do it for the host specifics, like what is the next hop, it will be like uh, always the similar one. Uh, so based on this, we have two way of routing. Mm, there's something called autonomous system where we say like corresponding to an administrative domain. Internet is not a single network. These autonomous systems reflect organization of the internet, e.g. Stanford and large companies. The goal of this autonomous system is to choose their own local routing algorithm, and they want to set policies about non-local routing, and each autonomous system assigned unique 16-bit number. Uh, the autonomous traffic is the packets with the source and destination in local autonomous traffic, and transit traffic passing through the autonomous system. There is stub AS that connects to only single other autonomous system. And there is like transit and multi-head autonomous system. Inter-domain routing. uh, I'm not sure. So inside this autonomous system, there is two way of routing. That is intra-domain routing algorithms. One is distance vector, and the second one is linked state routing. I think did I discuss? Let me see. Transit. Transit autonomous system. Yeah, I think I discussed question number 3 as well. So based of yeah, I discussed this as well. Anyway, so in this type of routing, we have two intra-domain routing. Uh, uh, One is distance vector, and another is link state. If it is intra-domain, that there are two types: distance vector and link state routing. If it is inter-domain, there is called path vector routing, that is also called BGP. In the distance vector routing, each node shares its routing table with its immediate neighbor periodically, and and when there is a change. So So like let me uh, how do I explain this? Cost to next. A cost zero next. Mm. To E cost is 6. Okay, so A is stable, D stable. Yeah. So E cost is infinite. Why? In the writing of tables. B3. Hmm. Uh, I think I should discuss the link state routing. Okay, distance vector routing concept. Uh, and C. I might have to show you the slides. It's better to show in the slides than to say the link state routing. C, A, cost. Yeah. So let me share this screen. So if you see this distance vector routing, so first let's see this distance vector routing, then we'll go for the link state routing. The distance vector routing, let's say this is an example of the internet, and like you are having this thing. Um, so let's say the load that you the cost of transferring file from A to B is 14, A to F is let's say it's 78, and so on and so on. So what you're doing is that so everyone periodically send its knowledge to the neighboring host, So I critically send my knowledge about whole network to A and C because A and C are the immediate neighbor of this. Similarly, A send the same thing to B, F, and E. D send the thing to E and C, and F send it to A, and so on. So in the first this is the first iteration. In the first iteration, A knows that to get to D, I need to have three load. So like if you see in the A's routing table. So let's start about B. So if you have to go to B, you don't have to go to the next hop anyway. You just have to uh, take this route, and with the cost of 5, you will reach B. So if you go to A's table to reach B, yeah, the cost you have to pay is 5, and next hop is none because the direct hop is B. To reach A, you have to pay 0 cost because you are already at A. As it is A stable, and the next is none, and like undefined. For C, there is 2. For D, there is 3. For E, it's infinite. Why infinite? Because E is not the direct number of A. That's why we just put in. We'll just see in the next address. Similarly, if you go to C stable, in C, it knows how to reach A, how to reach B, how to reach E, but it doesn't know how to reach, also know how to reach C because it is the C. Doesn't know how to reach D because there is some direct connection about it. That's why you just put infinite and leave it blank. For D, however, everything is infinite, like reaching, it will know reaching itself, and the A, every other thing is infinite. If you go to the next hop, like next iteration, and look at A's table. So what it does is that it just takes so it just look at the routing table from the neighboring states, and takes from D and E. From D, it is not able to get much because from D you cannot reach E. So E's field is still infinite. But if you go to if it gets B stable, so this is okay. So if you get from C stable, so this is you received from C. So in from C, you get all these things like from C to reach A, you have to if you use C as the next hop or as the next host, then these are the value you'll get. So then it will compare it with its own table and see which one is better. So you see, from A to reach A, the cost is 0, but from A to reach A through C, if you take the next step as C, the cost is 4. So I'm gonna keep this one. That's why you keep this one. Similarly, if from A to reach B, you have to this is the A's old table. You have to earlier you have to pay 5 cost as 5, but now if you have to go through C, the cost is 6. Since this is the lowest cost, I'll keep this one. So it keep like this. If you compare it like this till the end, see, to reach E from A was earlier infinite because there was no direct path, but here if you go through C, the cost is 6. So since 6 is less than infinite, it will take 6 as the um, um, valid cost through C, and it will get stable at the end. This is distance vector routing, and there is the instability that comes with distance vector routing. That is, let me see. Yeah, there is instability that comes with distance vector routing. That is, if a connection breaks, so then, since the um, um, A has a like A has a so if this connection breaks, the A will have infinite distance to X. Uh, A receives update from B, and yeah, so it will. So let's say A receives update from X, and X is 2 away, and B receives update from A, that is X is 6 cost away, given that we are going through A because it's 4 plus 2, 6. Since if this connection breaks, this will be infinite, and then if it will look at B, it will like the cost of going to X through A is 6. So then it will then this A will update that, okay, So if I go to B as a next stop, then come to A, then come go to X, the cost will be 6. Then if I go to X from myself, it will be 6 plus 4, 10. And similarly, this B will update next to 14 and so on. Finally, it will be infinite and infinite, which should be who should have been initially figured out. The next thing is three node instability, where if the connection breaks here, then like no, if it is the initial one, like two, the cost, the go to the uh, sorry, the connection to the x cost 2. This connection breaks, this becomes infinity, and B sends router to A, so it will say, okay, no, it is 8 uh, uh, miles away, and uh, then sorry, so it will be infinity first. After A sends the routing table to B and C, but the packet to C is lost. Uh, yeah, so I mean, automatically it will be updated among themselves using the lowest one, and the cost will be coming out to be like, the route to X will be 12 away, and so on. That is one of the method, like linked state routing. Sorry, the distance vector routing. To solve this, we got a linked state routing. In linked state routing, we send every packet information to all the neighbors. So I send information about my neighbors to every router. So it will send the information to all the routers, like flooding with packets. It will not selectively send the packets. So the routing table for this, like, if you look at the routing table for all these things, A state of link will be 3, 2, and 5. C's will be 2, 4, 4, and so on. The routing table will look like this. So it will be created. The shortest path will be created based on this Dijkstra algorithm. So the routing table will look like this. A's to go to A, from A's routing table to go to A will be 0. B to the B to your cost. A to B will be 5, A to C will be 2, A to D will be 3, A to E will be 6. I think there is a question regarding this one. What will be the routing table for C? So if you see C to A will be 2, C to B will be 1, C to C will be 0, C to D will be 6, C to E will be uh, 4. Okay. But yes, your job is to find out which will be the next hop for going to A through B, and what is the next stop for going to B? What will be the next stop for going to C? From C to C, what will the next stop? That will you don't need to fill the third one. But what is the next stop if you go to D? What is the next stop if you go to E? Okay, so you have to fill that. That is your question. Uh, hmm, okay. I think I covered this one as well. This fourth question as well. I think I need to cover this BGP algorithm, or I can just skip it. Open shortest path first. I don't need to cover this. This is directly in the slides. You can pick it up. For type of routing, you just add this also in the slides. I guess you can pick it up directly from the slides. I think I just need to explain the BGP algorithm. Let me share my this screen. Close my this. Give me a minute. Sorry. I think the BGP one is too long to cover today. Everything. There's Mrs. Format and all the stuff. I'll just. Uh, it's too big. It's like if there is different autonomous systems like this big organization, the routing that is happening inside the organization is controlled by this two algorithms that is uh, uh, vector link state routing and distance vector routing. But the routing that happens between two autonomous systems is done by BGP or the that is called bo- border gateway protocol. Uh, Let me see the question. I might. Uh, okay, so I think question number six is covered now. Like which is true for BGP routing protocol? It's an inter-domain routing protocol. False. It is not an inter-domain. It is inter-domain. It's a type of link state routing protocol. No, link state routing protocol is an inter-domain protocol, not a inter-domain. BGP replaces IGP protocol as in an AS. BGP relies on IGP packet forwarding between IBGP peers. I think the fourth one will be correct for this, but I'll not tell. Yeah, so I think I covered question number six as well. What is BGP is basically the question. But for question number six and five, you need to go through the slides and check. Question number 10 also you can answer if you have listened to the this next talk like distance vector routing and the CIDR notation. I'll try to cover the BGP one next week if possible. Otherwise, we will. Otherwise, you can try going through the lecture once and try to figure them. If you couldn't, you can put it in the announcement sections, and I will look into it. Um, uh, and might answer you there as well. Uh, uh, then yeah, so all these videos are uploaded to my YouTube channel. So you can have a look at that if you want. Uh, but yeah, but yes, I'll just share this link here on the chat window. If you haven't subscribed, you can subscribe and look at the videos. But yeah, I'll stop the videos now, and we will meet next week. Thank you.